So in these launch projectiles, we're going to have initial velocity that is both horizontal and vertical. So we're just going to start right in with problems, right? It's essentially the same, except now we're going to have to solve for VYI and use VYI in our problems. We're still going to use the same projectile equations that I gave you last class, right? Did you write down the two sections of projectile equations, both vertical and horizontal? Okay, so we've got that information, and we're going to use all of that to solve these as well. So I'm going to start by drawing a little diagram here of what's happening in our motion. It says, I punt a football in the air at an angle of 40 degrees with an initial velocity of 4.2 meters per second. What are the velocity components of that vector, right? All that it's asking right now to do is to break that vector into x and y. Do you see how it just says the angle is 40 degrees? Do you have any questions about that? 40 degrees what? Right? We assume when a cardinal direction is not given like that, we assume that our angle is from the horizontal. So our 40 degrees would go right there, right? We're going from the horizontal and we're coming up, right? The positive horizontal and we're coming up 40 degrees. And so if my initial velocity, or VI, equals 4.2, what would I call that side right there? Is it the y component or the x component? Right, I would call this VIY, and I would call this side VIX, or VXI, or VYI. Whatever order you want to put the subscripts in doesn't matter. Sometimes I end up mixing them around. But as long as we see the initial and then the component there. Now, I want to talk about one thing right here. It is so important for us to understand that this right here is a really, really zoomed in portion of time, right? This is just the initial contact of that ball. Because after its initial contact, right, it's going to go upward, it's going to go up, and it's going to come back down, right? It's only moving at a straight angle like that for a split second, right? And then it starts its arced path. It moves both horizontally and vertically. So we need to understand that this right here is a really, really zoomed in kind of portion of that motion. Does that kind of make sense? It's also really important for us to understand that this side right here, it has nothing to do with the height, or this side has nothing to do with the distance it travels. It is simply the components of that initial velocity vector, okay? Just because, I'm just going to make up a number that goes right here. That's not the number. But if this number was 1.4, we would not say that this object reaches a height of 1.4 meters, right? That is not the case. It has nothing to do with how high that object is going. It is simply the vertical component of my initial velocity. Does that kind of make sense to everybody? Because sometimes we get caught into these triangles and we see like, oh, that's it, right? But it's not, okay? So let's go ahead and solve now for the components of our vector. V1 or VIY, initial vertical velocity, am I going to use sine or cosine? For y, am I going to use sine or cosine? Sine, because it is opposite and I have the hypotenuse. Okay, so actually, let me do that again. I always do x first. I don't know what I'm thinking here. I always do x first, okay? So for x, I'm going to use cosine. So initial velocity x is going to be 4.2 times cosine of 40 degrees. And we said V1 or VIY is 4.2 times sine of 40 degrees. Okay, go ahead and plug those in, please. And see what we get. So tell me, what do we get for the x component? Say it again. 3.2. Does that component need to be positive or negative? Positive, right? It's moving forward. And then our y component, what do we get for our y component? 2.7. Is that what I'm hearing? Okay, and that positive or negative? Positive. Okay, that's it. That's all that this question is asking me to do, is find the components of my vector. Now, if I were going to continue a projectile problem with this, these are the numbers I would use, right? This would be VXI and VYI. I would never, ever in my problem use 4.2. once I break down that vector into x and y, I would never use 4.2 in my problem, right? Because nowhere in my projectile equations does it just ask for vi, right? It asks for vxi or vyi. Are we on the same page with that? Once I break that vector down, I think for some of you it might be helpful to literally cross it off, right? I'm not going to use that 4.2 anywhere. Yes. So now let's move into a full problem. Okay, it says a football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. Calculate the maximum height and the time of travel before the ball hits the ground again. So we've got two different things we're solving for here. Again, I like to kind of draw a diagram, and you'll see here, I draw my initial velocity really zoomed in. Okay, so there's my 20 meters per second, and my angle is 37 degrees. Okay, and then you can go ahead and draw the rest of that motion if you want. That's really up to you. You don't have to, but we need to understand that that's a really zoomed in version or picture of our initial motion. Okay? So what would I call that side right there? What component is that going to be? Good. Okay. Sorry, let me write that in there. This would be V, Y, I. And this bottom one right here would be V, X, I. Okay, so now let's go ahead and solve for those because we know we're never going to be able to use 20 in our problem. We have to have the individuals. So VXI, I'm going to use cosine. 20 times cosine of 37 degrees. And that gives me, I'm going to round that to 16. Okay, and then VYI is going to be sine of 37. And that gives me, I'm going to round that one to 12. Okay, and both positive, right? Because we're moving them forward and upward. So are we on the same page with that so far? Okay, so now we've got to figure out here. It asks me to find the maximum height. And so where along my path would I find maximum height? Right here. Right? And so I want to talk about a couple things here. We talked about how our horizontal acceleration never changes, right? Horizontal acceleration is constant. And I want you to think about this. As it travels in its arced path, what happens at its highest point? What do we know happens at its highest point? Okay, so tell me what happens. At an object's highest point, what do we know so far? At a highest point, what happens? What does it do? It stops, then it comes back to zero. But in a projectile, when it reaches its highest point, does it just drop? No, it keeps moving forward, right? It keeps moving forward, and then it starts speeding up in the vertical direction again and starts to fall. But it's important for us to realize at our highest point, our Y final equals 0, but Vx final does not equal 0, right? Because our Vx is constant all the way through. Okay, so at our maximum height, our Vy final does equal 0. Are we good with that part, right? The object doesn't just drop, it stops moving vertically, but it doesn't stop moving horizontally, okay? So tell me, what variable are we solving for if we're trying to find maximum height? Okay, yes, but not x. We would probably, since it's vertical, call it y final, right? Solve for y final. That's going to be our question mark, okay? And we already said we know at peak height, Vy final is equal to 0. Okay, so now I've got to figure out, do I have an equation with just this information to help me solve for y final? I agree. I would, not the second vertical, sorry, walk that one back. Second vertical, because we don't have what yet? We don't have time. So what equation doesn't have time? The third. I think the third will work, right? So if I go use the third vertical equation that says VYF squared equals VYI squared plus 2AY final. And what do we always know about A in the vertical direction? Yep, it's negative 9.8. Okay, so now we can just go ahead and plug in our numbers. Vy, bless you, 0 squared equals 12 squared plus 2, negative 9.8, and we're solving for y final, right? What this equation is telling us right here is we're trying to find at what height does my final velocity equal 0? And the only place where my final vertical velocity equals 0 is at the peak height, right? This equation that we're setting up is asking us at what displacement does my final velocity equal 0? And that has to be our peak height, okay? So let's go ahead and solve that for y final. That's what I had, 7.35. Is that about what you had? Or no? I'm getting wide eyes. Did I do math wrong? Yeah? We're going to take 12 squared and subtract it over, then divide that by negative 19.6, right? Because we don't have like terms on the right, so we can't combine that. We've got to move that over first. All right, so that tells us our object is going to reach a peak height of 7.35 meters. The second part of our question asks for how long is it in the air? What's the time of travel before it hits the ground again? So if I want to solve for time, I've got to take a look at my equations and figure out what equation do I have that would allow me to solve for time. Okay, so tell me, how would I use the first one? Because there is a way, but would that get me total time? Bingo, that'll give me the halfway. So is my motion here symmetrical? Is it going to start and end at the same height? Starts at the ground, ends on the ground. So that shortcut method will work. Okay, let me walk you through what I mean here. If I don't know my final velocity at the end of my motion, which I don't, I would have to use the second vertical, right? Y final equals y initial plus vyit plus 1/2 at squared, right? I'd go 0 equals 0 plus 12t plus 1/2 negative 9.8 t squared, right? And I'd have to go quadratic. But we already kind of discussed that we don't like the quadratic, right? So if we don't want to use the quadratic, we do our shortcut method. And that would mean to solve for the time it takes to go from start to midpoint, solve for t, and then we would multiply it by 2 because it's going to take the same amount of time to go up as it does to come down. So that's the method I recommend, especially, it only works when our motion is symmetrical, okay? If we start and end at the same height, that method won't work, okay? We've got to make sure that we are starting and ending at the same height to be able to do that. So I'm going to solve for time it takes on the way up. So that means I can use final velocity equal to 0. So 0 equals 12 plus negative 9.8 times t, right? I'm using my first vertical equation to solve for the time it takes on the way up. And that gives me a time of equal to 1.22 seconds. This is only the time it takes to reach the peak height. So I multiply that by 2 and I get 2.44 seconds. All right. So same football, but now we're punting it from a meter off the ground. We're set our initial positions as 0. Okay, that should be x, I, and y, I as zeros. We know our vxi and our vyi from previous problems. So we're going to be able to solve now for the time it takes to hit the ground and then solve for x final. Okay? So let's talk through this again. My object is not being kicked from the ground this time. It's being kicked from a height of 1 meter. So it's going to land below where it started, right? Here's my origin. It's being kicked and it's going to land below where it started. So do we expect our time of our travel to be greater than 2.44 or less than 2.44? It's going to be a little bit greater, right? Because it's going to have to travel that 1 extra meter. You know what I'm saying? If it were going to start and end at the same height, now it's not. It's traveling 1 more meter. So it's going to be barely longer, but it's going to be longer. So we've got to solve for the time it takes to do this whole path now, and then we can solve for x final. So let's remember here what our variables were from the first part of our problem, okay? Vxi was equal to 16, and Vyi was equal to what, 12? Okay? So my goal this time is to solve for my x final. Right? I want to find out how far it goes. Now, if you look at your horizontal equations, the only one I have that I can use would be x final equals x initial plus Vxi times t. So I have to have time. And we already said we can't use the time from the previous problem because it's going to fall a little bit extra. Okay, so here's what I'm going to say now. We're going to have to either use the quadratic or bypass the quadratic because my motion is no longer symmetrical. I'm not going to be able to multiply my time times 2 because now I've got an extra segment there at the bottom, right? So do you want to use the quadratic or bypass the quadratic? Okay, so if I go around, if I bypass the quadratic, do you remember how to do that? So if I want to bypass the quadratic, I need to find out how fast is it traveling at the bottom of my motion, and then I can calculate how much time did it take to reach that speed. So to bypass the quadratic, you use the third equation to solve for VF, then you can go use to solve for time. Okay, so let's do that. If we want to bypass the quadratic, we're going to solve for VYF. And we're going to use our third equation to do that. VYF squared equals 12 squared plus 2A. And what's my Y final here? What's my Y final? Nope. -1 meter. Right? Because my object is going to land 1 meter below where it started. Right? It left my foot at what I'm calling the origin. Right here. Right? Here's the origin. It's going to travel through the air, but it's going to land down here. Yeah, right. But final displacement is just how far is it from where it started. So vertically, right, vertical final displacement, it's just 1 meter below where it started. Okay? Yeah, so you're right. That's not the same as distance. Distance would be a total amount of traveled. Okay, so let's go ahead and solve here for VYF. Okay, I got my final vertical velocity as 12.8 meters per second. But I'm missing one thing on my final velocity here. It has to be negative, right? I've got to add that negative there because I know it's going downward. Okay, now I want to talk through just a conceptual thing here, right? Newton says that motion is, for every action, there's an equal and opposite reaction, right? For all of these things, our motion is equal. So that means if my object were to go, it leaves this punt, it leaves my foot traveling 12 meters per second in the vertical direction. If it were to land on the ground, my VYF would be -12, right? It goes up at 12, it comes down at -12. So does it make sense that it's moving a little faster by the time it goes that extra meter? Yeah, right? It's falling a little bit more. Gravity's acting on it just a little bit more. So it's a little bit faster by the time it reaches the ground there, right? Because it's got to travel 1 extra meter. Okay? So I've got my final final velocity. Now I'm going to solve for the time it takes to reach that velocity. And so that one is just the first. I can just use the first kinematics. Negative 12.8 equals positive 12 plus negative 9.8 times t. And that gives me a value of 2.53 seconds. Do I have to multiply that time by 2? Nope, because I took all that into account, that by the time I reach here, I'm going to be traveling negative 12.8 meters per second. Oops. Right, by the time I get there, I'm going to be traveling 12.8 meters per second in the negative direction. And so this is telling me it took me 2.53 seconds to reach that speed. Okay, now final thing we've got to do is actually solve for our x displacement here. Okay, so our x final is going to be equal to x initial, which we say is always 0. So 16 times 2.53. That gives me a value of 40.48 meters. All right, so that's how far the punt traveled from foot to ground. Right? It traveled a horizontal distance of 40.48 meters. Try this one on your own. A ball is launched 4.5 meters per second at 66 degrees to the horizontal. All that means is you're going to go positive horizontal axes and bring it up 66 degrees. So your angle is going to go right there like it's been in all of our other problems. What's the maximum height and the flight time? Okay, for problems like this where it doesn't say otherwise, we assume that our object is symmetrical, right? It's going to start and land at the same height.
Is that not a really small number?
It is. Yeah, so using the word launched is pretty generous, right? It's more like it plopped or something, you know? It's not like a real dramatic launch here because it barely goes a meter in the air.
Yeah,
or doesn't go a meter in the air, right?
I thought I was going
Nope.